Hi, this is Sudeep, and I welcome you back to this wonderful journey of learning structure analysis with STAAD.Pro. In the recent episodes, we had been solving for the reactions of statically determinate structures using equations of equilibrium. We had also modeled the structural problem in STAAD.Pro and had interpreted the reaction results out of the STAAD.Pro's post-processing mode. After that, we had compared the reaction results that we had obtained from our manual calculations using the equations of equilibrium with the results that we had obtained from STAAD.Pro. We will look into a similar problem today of a cantilevered frame, and we will solve for the reactions of that particular structure. But before we go forward, please do take a moment to hit the subscribe button if you are new to this channel and join us in this wonderful journey of learning structure analysis with STAAD.Pro. Today we will solve for the reactions of this cantilevered frame that you see on the screen. In this cantilevered frame, there is a horizontal member 3 meters in height and a horizontal member 1.5 meters in length. A load of 60 kilonewtons is inclined and is applied at the tip of the horizontal beam. The frame is fixed at the bottom. A fixed support would mean that this node number 1, as you see on the screen, would be incapable of both translations and rotations in the plane. If you want to know more about fixed supports, you can look into the session, the link of which is appearing on the screen right now, where I have discussed the characteristics of a fixed support. Now, the next step in this problem, of course, is to resolve the inclined load of 60 kilonewtons into its horizontal components. We know the gradient that is being shown in the problem statement. Now, remember that in the last episode, we had solved for a similar problem of a 60 kip load, which was inclined at the same gradient. So the numerical values of this force in the horizontal component and the vertical component would be the same as what we have calculated earlier, but in this case, instead of kip units, it would be in kilonewtons unit. If you want to have a look into that problem, you can go to that session by clicking on the link that is appearing on the screen right now. So, as you understand then, that 60 kilonewtons inclined load is now being resolved into its vertical component and its horizontal component. The vertical component is 48 kilonewtons acting in the negative direction of the y-axis, and the horizontal component is 36 kilonewtons, which again is acting in the negative direction but of the global x-axis. As a reference of the axis system, you can see that at the bottom right corner of the screen, where the faded blue arrow indicates the positive direction of the global x-axis, while the faded red arrow represents the positive direction of the global y-axis. The direction of the global z-axis would be out of the screen towards you. It would be coming out of the page towards you. Now, before we go forward, let us quickly revisit the concept of right hand thumb rule. So basically, if your right hand thumb is pointing towards a particular positive direction of an axis about which you are to calculate a value of a rotation or a moment, the positive direction of that rotation or moment would be given by the curl of your fingers. So in this case, where x and y are the plane in which we are working on, and the global z it would be coming out of the page towards you, imagine that the thumb is pointing towards you out of the screen, and thus any anti-clockwise movement or rotation would be considered as positive. Now let us consider to replace the fixed support with the restraint that it provides to node number 1. This typical figure, which is represented with the applied loads and the reactions, are called a free body diagram. So this is the free body diagram of this cantilevered frame model, or of this cantilevered post. Now we have considered the restraints to be in the positive sense. So the global horizontal reaction is pointing towards the positive direction of the global x-axis, and thus it's pointing from the left to the right. Similarly, the global vertical reaction at node number 1 is considered to be in the positive direction of the global y-axis, and thus it's pointing from the bottom to the top. And finally, the reaction, the moment reaction at node number 1 is considered in its positive sense. Now remember that with the given configuration of the x and y axis, the positive direction of the z axis would be pointing out of the screen towards you. And thus, if you consider the right hand thumb rule, any anti-clockwise movement or rotation would be considered positive, and thus the moment reaction is shown in its positive sense in the anti-clockwise directions. We have named the horizontal reaction as R1H, which would mean the horizontal reaction at node number 1. The vertical reaction as R1V, which would mean the vertical reaction at node number 1. And the moment reaction as R1M, which would mean the moment reaction at node number 1. Now, we can see that there are 3 unknowns, and as we know that there are 3 conditions of static equilibrium. So this is a statically determinate problem. If you want to know more about statical determinacy, please revisit the session where I had discussed this by clicking on the link that is appearing on the top right of the screen now. Now let us solve for the reaction of this particular structure. In other words, let us solve for R1H, R1V, and R1M. So we'll apply the first equation of equilibrium, which is summation of the forces along the global x direction is 0. Now what are the forces that are acting along the global x direction? Well, it is the reaction R1H, which is assumed to be acting in the positive direction of the global y-axis. And then we have the applied load of 36 kilonewtons, which is acting along the negative direction of the global x-axis. So this would mean that R1H, which would be positive, and 36 kilonewtons will be taken in the negative sense. So if we sum that up, it would be R1H minus 36, and the summation has to be 0, which means that R1H would be 36 kilonewtons. Now, R1H equal to 36 kilonewtons is a positive value, and thus the reaction or the direction of the reaction of R1H that we have assumed is correct. So we can now write R1H is equal to 36 kilonewtons. The next equation of equilibrium that we'll use is sigma Fy equal to 0, or the loads acting in the vertical direction of the global y-axis would be 0. Again, the forces acting in the vertical directions are R1V, which is the vertical reaction, and we have assumed that to be acting in its positive sense along the global y-axis, or the positive direction of the global y-axis. And then there is the vertical component of our inclined load, which is 48 kilonewtons, which would be acting along the negative direction of the global y-axis, and thus 48 will have a minus sign before it, and if we sum that up, it will be R1V minus 48 would be equal to 0, and if we solve for that, we will have R1V equal to 48 kilonewtons. R1V being evaluated to be positive means that our assumed direction of R1B acting in the positive direction of global y-axis is correct, and so we can write R1B equal to 48 kilonewtons. The final equation that we'll use is the summation of mz1 equal to 0. So we are taking the moment about the global z-axis. Now again, remember that the global z-axis is coming out of the screen towards you, and we are taking the moments of all the forces at point 1. So what are the forces that are acting about point 1? Well, the first moment would be the reaction moment, R1m. We have assumed that to be acting in the positive sense, in the anti-clockwise direction. So R1m would be positive. Next, we have if the load of 48 kilonewtons, which is acting at a horizontal distance of 1.5 meter away from node 1, and this would create a clockwise moment about point 1. So we will have a moment of minus 48 into 1.5 meters. Again, we have the horizontal load of 36 kilonewtons acting at a distance of 3 meters from node number 1. However, the moment that this load would create about node number 1 would be in the anti-clockwise direction, and hence it would be a plus 36 into 3 kilonewton meter of moment that would be applied. Now if you sum all of this up, we'll have R1m plus 36 into 3 minus 48 into 1.5 equal to 0. And if we solve for this reaction, we will get R1m as minus 36 kilonewton meters. So we'll have to write R1m as minus 36 kilonewton meters. Now, what does this mean? What does a minus 36 kilonewton means? It means that our assumed direction of the application of this reaction moment, which was in the anti-clockwise direction, is actually incorrect, and it would be acting in the opposite direction, and thus we will have the reaction moment to be acting in the clockwise direction. Now let us discuss about how we would model this in STAAD.Pro. Now we have seen that the units of loads are in kilonewtons and the units of length are in meters, so we would need to adopt a kilonewton meter unit system in STAAD.Pro. If you want to know more about the unit system of STAAD.Pro, you can refer to the discussion, the link of which is appearing on the screen right now. Now on the right side of the screen is the computer model that we intend to create, and the first thing that we intend to do is to have node number 1 at the global origin. Thus, the location or the origin of the global x and global y axis will start from node number 1. So this would mean that the coordinates of node number 1 would be 0, 0, 0. And now since we are defining the units in the length units in meters, so all the coordinate units would be in meters. So what would be the coordinate of node number 2? Well, the coordinate of node number 2 will be 0, 3, 0, since node number 2 is directly above node number 1 by 3 meters. And then node number 3 will have a coordinate of 1.530 because node number 3 is directly at a horizontal distance away from node number 2 by 1.5 meters. So once we have defined the coordinates, we define the member incidences. So we'll have two members, one member defined between node 1 and node number 2, and the other member defined between node 2 and node number 3. And then we have to apply the loads at node number 3 in the respective directions. And finally, this is before the load case, you would need to also model the support at node number 1 for the fixed condition. Now, we will quickly see how we can model this in STAAD.Pro. Now, since our units are in kilonewton meters, we need to ensure that our base units are set to metric unit, which it is, and then we need to go forward. If you want to understand more about the base unit settings, you can refer to the attached discussion, or the discussion, the link of which that is coming up on the top right of the screen right now. So now we want to create the structure. So we can say that this is a cantilevered frame, and we will create the stat file. And remember, we'll define the nodes. Our first nodes were 0, 0, 0. The second node was at 0, 3, and 0. And the third node was at 1.5, 3, and 0. So once these nodes have been created, we will define the member incidences. So for beam number 1, we'll define that it is being defined between nodes 1 and 2. And for beam number 2, we will say that it is being defined between nodes 2 and 3. Note that the beams has also been subsequently created in the viewing mode. Now let us go to the view option and view it from the front. So we are viewing it in the XY plane. And once we have done this, let us quickly define the properties. Now remember that in our manual calculation, since it was a statically determinate problem, we did not need the values of properties, but for STAAD.Pro analysis, you need to define the material and sectional properties. If you want to know the reason why, you can refer to the link of which is appearing on the screen right now. So let us click and let us say that, okay, we have rectangular sections of 250 millimeter by 400 millimeter. We are defining this in meter units. So we are saying that it is 0.4 meters and 0.25 meters. We click on the add button and we use an assign to view option and assign it to all the frame members. Once we have done this, the next thing, now remember that we have also defined the material as concrete. It doesn't matter for this problem. So we have defined this as concrete. Now let us go to supports, and we have to define a fixed support at node number 1. Just quickly to understand what are the node points. So I press Shift plus K, and then I press Shift plus N to display the node number. So this one is node number 1. So I say that I want to create a fixed support. I add it in the support hole structure box, and I use the cursor to assign it at node number 1. So node number 1 has now been defined with a fixed support. Now the next thing is the definition of loading. So we say that we want to add a load case, and we want to define the title of the load case. Let it be load case 1. We click on the add button and we say that we want to define nodal loads which will apply at node number 3. So remember that in our case, our X load was minus 36 kilonewton at that node, and our Y direction load was minus 48 kilonewtons at the same node 3. So we'll say add to that, and we will assign this load of which has a horizontal component of minus 36 and a vertical component of minus 48 to node number 3, and we have defined the vertical and the horizontal loads instead of the inclined loads in this case. We had directly defined the inclined loads in our last problem. So if you want to know how to define an inclined load directly, you can refer to that particular session. So I press Shift plus V to display the load numbers, and we can see that we have assigned the loads properly. And finally, we want to add the analysis command. So we add the perform analysis command. Now, what is the validity of this perform analysis command is something that I have discussed in one of the past sessions, and you can know about that by clicking on the link that is appearing on the screen right now. So click on the close button, and now we are ready to analyze this particular file. So we go into the text editor and check the inputs that is defined. So we have defined the units in meter and kilonewtons. And then we have defined the joint coordinates, member incidences. We have defined the material. We have defined the sectional properties. We have defined the supports. We have defined the loads. And finally, we have the perform analysis command. So we are all ready to go for the analysis. So if you run the analysis would run fine. And then we would need to go into the post-processing mode to view the results and interpret the results of STAAD.Pro, which we will do in the next session. We will continue this discussion in the next episode, where we will look into the results that we have obtained from the analysis of the model that we have created today. We will interpret the reaction results, and we will also try and interpret the statics check table, the results that is displayed in the statics check table. So I hope you have enjoyed the session today and you have learned something about the calculation of reactions using the equations of equilibrium. If you have, please to hit the like button and let this content spread out to many students who would be looking out for a similar content. I hope to see you in the next session. Till then, bye bye.